Welcome dear learners to the course Theory of Composite Cell. Today the lecture 2 is week 1. So, in the first lecture I have explained the basics of composites, that the composites may be fibrous or the orientation of fibers may be 0 degree, 90 degree or angle ply, specifically for structural application. Then I have discussed about the constitutive relations and transformation materials, that how to basically it is not a transformation material, transformation of tensors. So, there are application huge, I would like to say that extensive applications of shells in various fields, civils, architecture. Already we have discussed some of them, but specifically large span roofs, liquid retaining structures like water tanks, containment cells of nuclear power plants and concrete arc domes. The reason to discuss this special or specific application, that because the application of whatever in this course, the theory of cells, so we can understand, we can analyze these structures using the shell theories. In mechanical engineering, cell forms are used in piping system. Basically piping system is a cylindrical shells, then the turbine disc, pressure vessels, if you talk about that LPG storage tanks, or you will talk about that oil tankers or any kind of pressure vessels. In the aircraft, missiles, rockets, ships, all are excellent example of shell elements in aeronautical and marine engineering. If you see that this is the dome shape roof of a famous building, Infosys Pune, and then the famous Hawa Mahal in Jaipur. But I would like to say that why this, you can just look into their windows and doors. So, it is a arc type, dome type. Any ancient buildings and very, you will find that they are in half arc form. So, basically it can take more load and it also looks beautiful. The reason is it can take more load. So, if you have a flat system, then it is, we require more thickness, but if it is in curved one, so with the less material it can take more stresses. So, the reason behind that why cell structures are used, that it has efficiency, means it is excellent efficiency of load carrying behavior. Very famous example, if this is a thin sheet and a corrugated sheet, when you have some structures, aluminum, steel for a roofing purpose. So, basically this curvature makes them more stiff, even the thickness remains same, but for a roof or a structure, so these corrugated sheets are preferred mostly compared to just flat sheets. So, they cannot take more load. So, just because of the curvature they have a more load carrying capacity. Then high degree of reserved strength and structural integrity. The most important part, high strength to weight ratio, because they can take more load. So, we can go thinner sheets, we do not need thick sheets, very high stiffness. And then the containment of space, basically a sphere, you know that it can have maximum volume compared to other bounded volumes. So, shell structure support, if you talk about just a square, so basically it will hold larger volume than just a cuboid structure. Cell structures support applied external forces efficiently by virtue of their geometrical form. That is the main reason, is that spatial curvature. If this curvature is not, so it cannot support. So, because of this curvature they are more stronger, more stiffer and other structural forms. So, let us come to the our topic, that how do you define a shell? Sometimes students have confused that the difference between plate and shell. A plate, like mathematically we say these both two are two dimensional or three dimensional body, we can say let us talk about thin shell or thin plate when thickness is very less compared to length and width. Same is true with the shell, that thickness is very less compared to length and width. But the important part is that in the case of plate, the surface is flat, there is no curvature. But in the case of shell, there is curvature. Curvature may be in one direction or two directions. Basically, the shell theories or the governing equations are derived in terms of middle surface or reference surface of the cell. That is the most important part in case of shell theories, middle surface. Sometimes we called it reference surface. So, now cell is defined in terms of a reference surface, that it is a body that is bounded by two closely spaced curved surfaces, where the distance between the surfaces is small in comparison with the other body dimension. In this figure you see that red one, red enclosement, it is a reference surface or middle surface. If you make another surface, let us say plus h by 2 and bottom minus h by 2 and close it, so it will become a shell element. A shell can be considered as a materialization of a curved surface. Is very I would like to say that essential component, that it should be curved, its surface should be curved. It may be in one direction or may be in two direction, but it must have curve. Like beam and plate can be considered as a materialization of a line and flat surface. For example, if you say that in designing extrusion or revolution, so basically plate and shell, there is a flat surface and then you can extrude it in the third direction. But for the case of shell, it should be some curvature and then you extrude it, it will give you a finite element or a shell panel kind of things. Then how do you define that a particular shell is thin, thick, what are the basis? So, basically this thickness divided by the radius of the cell. Generally, if it is a doubly curved surface, so we will have two radius R1 and R2. So, which radius? A smaller radius we are going to put it here. For example, if we have a cylinder, then in one direction radius is R, the other surface is flat, in that direction radius R2 is infinity, flat line. So, that thinness can be find it out h by R, not h by infinity. Let us see that how do you define a thin cell or a thick cell if h by R is less than or equal to 1 by 10, or vice versa, if you want to write R by h is greater than or equal to 10. But generally we used to write in terms of h by R, if it is less than or equal to 1 by 10, then it is considered as thick cell. For a thin cell, h by R should be, I think, in between, basically less than or equal to 120, or I have to write greater than 110 and like that. So, that is known as moderately thick. very thin, so it will be 1020. So, H by R ratio will be between 1000 and 20. So, generally it has been found that for a large number of practical application, thickness of the cell lies between this. So, specifically H by R most of the cases is equivalent to 1 by 100 and 200. That is the reason that thin shell theories are preferred mostly to analyze the behavior of shells. But there may be some applications like machine components or turbine discs where that thickness is not small compared to its radius. Then definitely we can go for thick shells. But in nature and different applications, 99% cases shells are thin. So, in the literature, a number of shell theories have been developed for the thin shell cases. As I have discussed that based on the curvature or based on radius of curvature, basically curvature is nothing but inverse of the radius 1 upon mu r. What does it tell? It tells you that how deep is this. For example, a flat surface, the radius is infinity. So, 1 by infinity gives you 0. So, it is flat surface. If it is very far, so it will be slightly shallow. If it is deep, near, like that, circle, very small circle. So, it tells you that our shell is basically, it is a measure of deepness, whether shell is deep or a shallow or a flat. So, based on the curvature, we can define cylindrical shells, conical shells, spherical shells, ellipsoidal, parabolic, cycloidal, toroidal and hyperbolic shells. So, these are different type of shells. So, in this course we will develop a generalized governing equations so that we can get the special equations for all kind of shells. The fundamental features of a shell, what are the basic entities or the variables? Very first is the reference surface. So, blue line is a reference surface. So, shell geometry is defined by its reference surface. So, whatever the form of reference surface, we will say that just above and below we will add the thickness and then the shell will be formed up. So, the shape or the curvature given to the middle surface is define the shape of a shell, then the thickness of the shell. So, in one direction radius is R1, in second direction radius is R2. These top and bottom surfaces are known as bounding surfaces. So, I would like to explain the things that reference surface, it is the most significant feature of the shell. It defines the shape of the shell. The behavior of the cell is governed by its reference surface. That is the important part, that if we are making some error or defining a reference surface, then the theory will not be accurate. So, you have to define the reference surface accurately. If the cell is composed of a single homogeneous material, then middle surface is selected as a reference surface. If we talk about shell is made of isotropic material and there is no variation, so we can say that middle surface will be equidistant from the bounding surface, is known as reference surface. If a cell is composed of many layered materials like composite materials, which is our study part here, that a neutral surface can be considered as a reference surface. Once the reference surface is selected, then shell can be defined completely. That I have said that very first step, that select a proper reference surface. Like for a cylindrical shell, for a conical shell, for a spherical, first you have to define a proper reference surface, then you can proceed further. So, already we have told you that what is the thickness, but I would like to emphasize that it is determined as the distance between two bounding surfaces. It is not always that this thickness will remain same, it is no boundation. It may change if we go from one here to here, but from the middle surface, upper bound and lower will be from equidistance. Let us say going from here to here, my surface is going like this. So, same way my bounding surfaces will be up and down. So, measured along a normal to the reference surface that passes through a point where thickness of the cell is being measured. Thickness need not to be uniform, it may be linear or a constant function of position in the most of the practical application. So, it is not that thickness is measured from other some references, from every point normal to that, from two bounding surfaces, this will be the thickness, and here again, and so on. Geometry of a shell is entirely defined by the middle surface and thickness of the cell at each point. We have to clearly define that how thickness will changes, either this is uniform or it is changing or it is a constant function. It may be same or it may not be. You see the figures of natural cell surfaces. So, these we call it these shells, and you see that different shell structures. I have just taken a one like patch and magnified it here. I want to show you that these are the lines, curved lines, that later on I will explain. So, if we want to study a shell, so we have to prepare a reference element and these grids. So, along this also, whatever the curvature will come, and then we will define some parameters and finally able to understand or develop a governing equations. So, very first concept is that principal directions or lines of curvature, like in here these are the lines of curvatures which you see on the cells, on the natural cells. Though they are in these surfaces, they are acting as a stiffener, they are making shell is stiffer because here thickness is slightly more compared to base thickness. So, these are also known as lines of curvature, curvature lines. So, consider a small region of a smooth surface. Let us say we take this surface or this. So, in this figure that a shell is described here and it is domain is omega. So, there were lines like you see in natural surfaces, so many lines will pass through. So, it says that let us say at any region, but we have taken a top or you can take any point, a point M, and at this point the surface is smooth. Then what do you mean by the smooth? It means surface is continuous and there is no discontinuity of slopes, no vertices. We have to select a area where it is smooth, no vertices, no discontinuity. Maybe like if you talk about cone, we cannot take because here slope is changing, surface is not continuous, this is making a vertices. So, we can draw various curve along the surface through this point. So, from this point we can draw various curve like this 1, 2, 3 and so on. then the tangent to this curve. So, every line before going to there, let us say in a circle, and this is my line. So, at this is a curve, and from here center to we are drawing a line. So, there will be two things, tangent to this, tangent lines, and one will be the normal. Same thing is here, over this surface, for each line there will be one tangent. Let us say for this line this tangent, for this line this tangent, for this line this tangent, and these are the tangents. So, then tangent to these curves are placed on a one plane, and that plane is known as tangent plane to the surface at M. For example, if you take any point M here and through that you pass all the curves and find out the tangent planes. So, for a particular curved line there will be one tangent, and all the tangent for all the curved lines will lie in one plane, and that plane is known as tangent plane to this surface. Now, a line perpendicular to this tangent plane. This is very important concept in shell, that the concept of surface normal, not the just normal. In a curve, in a one dimensional curve or in a 2D case, so it is the tangent and this is the normal direction, outward normal or inward normal. But in a case of a shell or a surface, it will be a tangent plane, and a line perpendicular to this tangent plane will be denoted by N, and it is known as surface normal. So, it is not normal because each curve may have one tangent and normal, but over this plane there will be one normal. So, that is known as surface normal. Since surface is smooth and tangent plane, hence the normals are uniquely determined. There will be single normal, it will be not that so many normals. So, now I have discussed two things, one tangent plane, tangents and surface normal. I am going to write it here. Tangent planes, basically tangents, then tangent planes, third is surface normal. Basically normal to tangent plane. It is denoted by N. Now, we say that, let us say this is one normal. Can we draw the sections, means cutting sections which passes through this normal? This is, let us say, our surface, which I have drawn already, and this is our normal N. Can we draw a section plane which contains this normal? Yes, basically the curved lines through which it is going. So, we can say that this is the one of the section plane which cuts that surface. So, we can see that we can draw infinite normal sections which will have the normal and cutting this surface. So, it is written that an infinite number of different normal sections may be drawn through the point of a figure. Here the concept of basically radius of curvature is explained. Then after that I will come to that principal sections, principal normal sections. So, I would like to explain it here that for each normal section there will be one radius of curvature. So, the radius of curvature is denoted by kappa. Okay. For let us say this for one for this for 2, this for 3 and so on, k infinity. For each normal section there will be a corresponding radius of curvature. Now it concept comes that principal normal section. So there will be at least 2 normal sections for which one will be maximum and one will be minimum. So the corresponding the maximum radius of curvature will be known as principal sections. That is the concept. Principal section planes, normal section planes. So before coming to this concept, the radius of curvature comes into the picture. How do you define a radius of curvature? So first of all, we will see through a circle, let us say in a circle, it is our center, and at any point it goes from here to here, this is our arc length and radius. Let us say it is d theta. So r d theta is your arc length, which is ds. So r is what? ds by d theta. It will give you the radius. If somebody tells you that arc length and the subtended angle, that change in angle, then you can find out the radius of that. So in one dimensional, a curve is there and it is moving from point M to M1 and making an angle d phi, and this change in angle from here to here will be d phi, and from here to here is s, and change in arc length is ds. Then rho, basically radius, ds by d phi. If we reverse it, kappa will be 1 by rho. So kappa is the radius of curvature. Inverse of radius is known as radius of curvature, which is written here, curvature. So basically we do not call it radius of curvature, we call it curvature, and previously we call it radius of curvature, means this is the radius basically, it is the जो भी curvature है, the radius of that curvature is rho, or in a circle it is r, it is ds by d phi, and the curvature measure of deepness is 1 by rho. So already I have discussed that an infinite number of possible radii of the curvature and curvatures at a point M of the surfaces, because an infinite number of normal sections may be drawn. So there will be 2 orthogonal normal sections, means perpendicular at any point of a surface, such that one radius of curvature is maximum of all possible, whereas the second radius of curvature is minimum of all possibles. So these normal sections are called principal normal sections or principal directions. Generally, the shell surfaces are defined in terms of principal normal sections and principal directions and curvature or radius of curvature. The curvature of these sections corresponding radii are referred to as principal curvatures. R1 and R2 are radius of curvatures, and kappa 1 and kappa 2 are curvatures, or sometimes we called it principal curvatures, and they are not vice versa. You can say that if kappa 1 is 1 by R1, then you can say that R1 is 1 over kappa 1. Anything you explain, vice versa. If you know the curvature, you can find out the radius. If you know the radius, then you can find out the curvature. So these normal sections are principal normal sections, principal radii and principal curvatures. Now we are trying to explain that parametric representation of a curve in three-dimensional coordinate system, rectangular coordinate system. Let us say a curve, red line curve is moving and the original system is defined that x1, x2 and x3, and it is moving from q to q dash. So, from origin the position vector is r plus delta r. Then the position vector can be defined as x function of t, where t is a parameter, sometimes it may be time or any other parameter. E1 is the unit vector along one direction, E2 is the unit vector along two direction, E3 is the unit vector along third directions. In the case of curves, basically we called it, I think if you are at undergraduate levels, that N and T, normal and tangent path systems, that it changes with the path, that curves positions are defined with the help of normals and tangents. So, at different locations they varies. So, basically the unit vector associated with changes along the path. So, that is why it is not constant, they are a vector, they changes along the length. Their magnitude remains same, but the direction changes. Then the concept of tangent unit vector. So, r is defined if you take dr by ds, that can be written as like this. Basically, we are interested to find out the definition of tangent vector, because we have seen a curve whose position vector is defined in such a way that x is a function of t, any parameter e1 plus x2, e2 plus x3, e3, you put position vectors, and the dr by ds, you find it out with respect to s is basically our parameters, curve parameters. So, we are going to find out dr by ds. Dr by ds is nothing but it is a tangent. So, we are going to prove it, find it out dr by ds, and the magnitude can be, if you dot product to this. So, ds square is nothing but dx1, ds2, dx3 in 3 dimensional. Then dr by ds is equal to 1. So, we can say that this is known as unit tangent vector and magnitude is 1. So, it is nothing but in 2 dimensional, you see, just for the case of a plate, if this is your length is dx1, this length is dx2 and this, let us say, ds. So, it will be ds square, curve length will be using the Pythagoras theorem, dx2 square. But for the case of curved one, it is not so simple. So, you have to find out this. So, it will be again ds1 and ds2 and this is ds. So, dx1, dx2 in 3 dimensional space, it is in 2D, same we can explain in terms of 3 dimensional case. We are interested to find out this for a curved one, what will be the ds. So, before that we must know what is t hat, unit vector, that it is defined by dr by ds. So, I have tried to explain that for the case of a circle, that e theta and er, unit vector along radial direction, unit vector along theta direction. So, they are a function of theta and they changes. So, basically dr by d theta is equal to, it becomes e theta, d basically del epsilon theta by del theta gives you minus of er. So, undergraduate level it has been explained nicely for the case of a cylindrical coordinate system. So, I would like to say that similarly here for the case of shell surfaces, these have curvatures. So, we can define the tangent vectors 1 and 2. Now, a concept of osculating planes. For example, that we have defined a tangent plane. Then we have also defined a normal section or a normal plane. So, perpendicular to this there will be another plane, that is known as binormal plane. If there is like direction in right hand thumb rule, or like two vectors A, B, when you are saying cross product of that, so it gives you basically direction C, perpendicular direction, it moves in that way. So, same way here, instead of just two vectors, here is a planes, that one is tangent plane and normal plane, perpendicular to that there will be a binormal plane. And there is saying that is binormal plane ke just opposite mirror image the plane will exist, that plane is known as osculating planes. Basically that plane will touch all these three planes, or the bottom mirror plane, which will have sometimes it is known as kissing plane also. Principal normal, already we have discussed that the normal corresponding to radius of curvature is maximum, it is known as principal normal. So, we know that the magnitude of a tangent vector is 1. So, the dot product of tangent vector will be 1. So, if we differentiate this with respect to S, so first if I explicitly write that first function as it is, differentiation of second function, and differentiation is denoted by just a dash, plus second function as it is, differentiation of first function. So, basically twice t dot t hat dash equal to 0. What does it mean? It means t hat is perpendicular to t hat dash. So, t hat dash is nothing but it is dt hat by ds. So, जो भी आपका टेंजेंट है, टेंजेंट वेक्टर, उसके परपेंडिकुलर एक वेक्टर एग्जिस्ट करेगा, दैट इज टी हैट डैश. वी आर गोइंग टू यूज दिस टाइप ऑफ basics later on. Initially we have to derive the basic relations, what is t hat, the meaning of that with respect to the curve. So, S is a curve length basically along x direction, S is moving. Then what is t hat? T hat is defined as dr by ds, which we have already initially defined, na? R defined, then after that we have defined t hat is dr by ds. If you know that R is a function of x and t, another parameter. So, t hat is dr by ds, but R is a function of t. So, using the chain rule we can say that dt by ds. Just before that we have said dt by ds. What was that? It was t hat dash. So, we can say that dr by dt will be time derivative or parameter derivative of r dot t dash. So, then we are differentiating this with respect to s. So, we will say that first function as it is, differentiation with respect to s, and then differentiation of first function, second function as it is. So, from there dr by ds again find it out, r double dot t as dash. So, finally we got this equation. So, the reason of deriving this equation, this will help us to find out the normal curvature. or the definition of a curvature, that how do you define a curvature in terms of a normal and some variable. So, the differentiation of tangent vector t with respect to s can be represented at second differentiation and first differentiation r dot and plus r dot. So, it is showing that the meaning of this equation 3 is a t hat dash is a linear combination of r dot plus r double dot. T hat dash must lie in the plane of r dot and r double dot, which is the osculating plane, definition of that. So, we can say that T hat dash is related to a principal normal and curvature. It can be written as some k kappa function and normal, unit normal. So, in the next slide it is clearly explained that T hat dash can be represented as vector k, which is a curvature vector, and k and this n is a unit normal vector. So, direction of principal normal to this curve at a point is defined. So, already proportionality of constant k is called curvature and its reciprocal is known as radius of curvature. So, basically it is called curvature. So, T hat dash can be written as curvature into unit normal vector. It is very important relation, we will use it later on. Now, come to the, let us say, define or a shell element which is having curvatures in both the directions, and alpha and beta are curvilinear parameters. These are the sub curvilinear parameters. So, from any reference you choose a point P, and the most important part, make a grid along the curves. So, let us say from here to here, this distance B to B1, B2, B3 and Bn. So, beta curvilinear coordinate takes value from B1, B2 and Bn up to n. Similarly, alpha, this is basically the curvature lines, we are drawing these things, making a grid over there, over the surface. So, these are the alpha takes value from alpha 1, alpha 2, alpha 3 and so on alpha n. So, basically you draw the line parallel to these, like that we have prepared. So, this is, let us say this will be d beta and this will be d alpha, change in small alpha, change in small beta. So, at a point P corresponding to, there will be two meeting curves. So, corresponding to this curve there will be one tangent and corresponding to this there will be one tangent. So, it is clearly, so from a position R we can define like this, but if we take a small increment, let us say this point P2 it moves to P dash, then we are interested to find out this ds. So, radius of curvature r comma 1. So, basically 1 means alpha and 2 means beta. So, here it is written as r comma alpha and r comma beta. Sometimes it can be written as r comma 1 and r comma 2. So, from position vector is r and position vector r plus dr. So, can we define that r or dr? So, every surface is rectangular coordinate system may be written in two parameters alpha and beta x1. Just go to back. So, here x, y, so basically it can be written as x1, x2 and x3, basically it will be x1, x2 and x3. They can be written in terms of curvilinear parameters alpha 1 and alpha 2. So, we can say that x is equal to x1, which is a function of alpha and beta. If you remember in previously, for a single curve we have said that x is a function of t. Now, I am saying for a surface, this x is a function of alpha and beta. x2 is also a function of alpha and beta, x3 is also a function of alpha and beta. So, position vector of any point at M on this surface can be given by this x1 E1, x2 E2, x3 E3. So, first we have defined a position vector for a single curve. Now, we have defined a position vector for a surface. Now, a differential change in position r hat. So, let us say it move to from point 1 to point 2, change in that dr position vector r plus dr. We are interested to find out what is dr first. So, dr can be find it out that del r by del alpha into d alpha plus del r by del beta into d beta. It is very simple. So, dr using the chain rule of differential that r is a function of alpha and beta. So, this can be find it out dr by d alpha into complete change in alpha plus dr by d beta into d beta, like that. Same way function f will be x and y, del alpha by del x into del x, del alpha by del y into del y. ऐसे लिखते हैं, we used to write like this, yes, small. So, dr can be written as like this, where dr by d alpha is denoted as r comma 1 and dr by d beta is denoted as r comma 2. So, it is the new equation, dr is r comma 1 d alpha plus r comma 2 d beta, that this is our ds and this is our dr. So, we say that for a smallest one, so it is going to be take the same. So, ds will be equal to dr of magnitude. It means ds square is equal to dr dot dr. So, you multiply r comma 1 d alpha plus r comma 2 d beta and multiply with that dot product. So, it becomes r comma 1 twice and d alpha square, then mixed twice of r comma 1 r comma 2 d alpha d beta, then r comma 2 d alpha beta 2. So, basically this quantity is replaced by E and this quantity is replaced by F and this term is replaced by G. So, this equation is known as first fundamental form of surfaces. So, this equation 9 is known as first form of fundamental surfaces. It allows us to determine the small change in the length and angle between the chords and area of the surfaces, which is a very first equation of the surfaces. Basically, what does it tell? Let us say these are the doubly curved surface and this is d alpha. We have moved very small and what is this change in arc ds square क्या होगा? So, ds square is, find it out in terms of r comma 1 is nothing but it is a tangent vector. So, E d alpha square plus 2f d alpha d beta plus g times d beta square. Again, if we say that E, F, G are called first fundamental magnitudes. So, ds1, that arc length along one direction is under root of E d alpha. So, over this the arc length ds1 and ds2, arc length in one direction, arc length in second direction can be represented by under root of E d alpha, arc length in second direction can be represented by under root of G d beta. R comma 1 and R comma 2 are the tangent to the curves of a constant A and B. So, basically for these curves, if you make a grid, so over that alpha and beta. If the parametric curves form an orthogonal net, that R1 comma is perpendicular to R2, then this 2f will be 0, because dot product of 2, if you talk about in rectangular coordinate system, I dot j is 0, I dot is 1, similarly j dot j is 1. So, I dot j is 0, when it is 0, because I is perpendicular to j. Same way, if tangent vector 1 is perpendicular to tangent vector 2, then we can say f is 0, and it reduced to a very simple form, 2 dimensional. Just when for orthogonal system, a1 d alpha square, a2 square d alpha 2 square. So, where a1 is under root of E, a2 is under root of G, because it is defined in such a way that a1 square, a2 square. These a1 and a2 are Lamé parameters. Sometimes we call it distortion parameters. Why we call it distortion parameters? You see that if it is a flat case, let us say dx1 and dx2. Now, you are saying my is slightly modified like that. Changing something. So, we are interested to that this change is change in basically arc length along S1, arc length along S2. So, this is your ds and this is your dr, or whatever say dr or something. So, this tells you this distortion in this. What is that? A1. A1 is a distortion parameter or measure of distortion. A2 is also a measure of distortion, arc length in along second direction. So, we can find out the arc length of a curved surface. And A1 and A2 are very important parameter to define the shell surfaces. So, basically the governing equations or the shell theories are developed in terms of R1, R2, A1 and A2. These are the 4 parameters, or sometimes you may say that kappa 1 and kappa 2. So, basically we need radius of curvature, then we need Lamé parameters. So, Lamé parameters is find out through the first fundamental form of surfaces, and if these our curvilinear parameters are orthogonal, it may be orthogonal, it may not be orthogonal. Generally for structural application we use that orthogonal curvilinear system where this can be 0. So, with this I end our second lecture. In the next lecture I will explain the second fundamental of surfaces, which is related to the curvature. Thank you.